Not kind of, no. Only that, only that. I haven't even had this one to I don't lie. Sometimes I forget that there's like formulas on the page, so I divide the thing from scratch. I've tried like from the like for this one. I really got mouse on that. Like dx over 3 times a, I don't remember the over 3 part. Yeah, don't forget your.
Well, welcome back, folks. Looks like we can get started. It's kind of interesting. My first class for the day is kind of flipped. Most people are on Zoom since it's mostly remote students, but for this class, most people in person. But glad the people on Zoom made it in today. For our work today, we're working through section 11.6. I think this is a pretty big section, so I didn't put in the next section down below. But another big reminder about where we're going on this week. This is week 12, and the week in the middle is our standard buffer week that we've been using ahead of every exam. And same for exam 3. Whatever we finalize completely as a section on this week here is going to inform us the last section on exam 3. And if you're curious, exam 3 also picks up on, let's see, we have exam 2 here, the solutions, the grade information. There's a 4-way tie for a perfect score on exam 2, so that was really pretty incredible. And let's see, we started on or ended on section 9.5. It looks like exam 3 is nice in a way. It's going to be sequences and series. It's really just how far we got into chapter 11 specifically. So really a very cohesive exam. That means almost as a guarantee, your handout for the notes on exam 3 is going to be this. But I'm going to shorten it up a little bit so that it's only going to include the actual stuff that we've got to. I'm not going to include stuff that we haven't gotten to. That'd be pretty weird. So imagine it'll be this list essentially with just the targeted stuff. I'll try to get that posted pretty soon since we're getting pretty close to the exam 3 week. And just like we had on our exam 1 week, exam 2 week, I'll be at the end of this week here, including information on the exact coverage, the formula sheet, and all the review type problems as well. So we're really just redoing that same exact structure. We also have some extra credit opportunities as well, since we're getting close to the end. After our exam week is a full-on review week, since our university is going back to a closed week policy. The extra credit opportunity is first all about homework, since homework is 30% of the course. If you go really hard on this right here, it's double duty. You're getting the 30% part of your course finalized up, and you're studying for the final exam all at the same time. Because the homework questions are really the routine questions that can come up on the final exam, except for the ones that got really long, of course. Other extra credit opportunity is more about if you had a bad exam day, maybe it was exam 1, 2, or the upcoming exam 3. If it was just a really off day for you, say for a hypothetical student, exam 1 is 93%, exam 2 67, exam 3 big rally up to 89%. If this happened to you and that exam 2 is really hurting your heart, you have an opportunity to make that up. The idea is if you studied on this content really well so that you came back and your final exam score is higher than your minimum score amongst exams 1, 2, and 3, then your minimum score is full on swapped with whatever your exam score was. If your exam score, let's say it was just a really bad day on the finals as well, nothing happens. Your exam 1, 2, and 3 is untouched. This extra credit opportunity can't hurt you. It'll only help is what this is saying. So, and just like with what's going on with the finals week, once we're in closed week, I'll be posting loads of information on practice problems, practice final exams, that kind of stuff. I'm thinking about this semester, including what a real final exam would look like. So like last semester's, maybe a prior semester, so that you can get a feel for how long is this exam. It's 2 hours long, so it's going to feel different. But seeing what the real exams really look like is a big help on that as well. Any last questions at all, folks, about any of the announcements at the moment? Okay, well, here's where we left off. We looked at these set of notes. We didn't actually start them at all, but here they are. We have ratio test and root test on this section. I mentioned before, these are really major tests. They're fast to use. Their conclusions are strong. Look what we get as a conclusion. If we do a limit of a particular ratio just right, the ratio of the next term with a nth term, if that ratio is controlled, it never gets above 1, it's less than 1, then your series was not just convergent. The last section alerted us to the fact that there is two forms of convergence, and one of them is a very weak form, which you can't do a whole lot with sometimes. But this convergence is the strong form. It means when we say that the sum here converges to a number, we really mean that in a literal sense, unlike with conditional convergence. Well, if it comes off to infinity, this is even better because a lot of our tests only go one conclusion, either just a conclusion of divergence or just a conclusion of convergence, like the alternating series test. But these tests are packed. We have convergence, we have divergence. Here's a problem though. It can become inconclusive. If the limit is exactly 1, we have a problem. So when this happens, if this ever happens to you, what you need to do is go back to this section, grab all of your other tests, because if a ratio test, say, fails on this one, well, you still have the alternating series test on the table for an example, or maybe just use the ordinary p-series test. So the idea with all these tests is, the reason we're pulling up this document even still is that no matter how many new tests we pick up, the basics are still majorly important. By the basics, we mean we always need to be fluent on test for divergence, geoseries, p-series, alternating series. These are nice when they work out, but the limit comparison test I would include as the next one amongst the basics. After that, these are the big ones, ratio root test, and this is, if all else fails, try the integral test. So let's give these a try. There's 3 different conclusions we can make. We hope for less than 1 for convergence. Here's a series. And to start this off, here's a great way to organize your work. We have to deal with an n+1th term and an nth term. If we call this summation an, then we're also saying at the same time, all of this is the nth term an. But literally writing this down on paper, it's helping your mind put together the total limit. Really great for partial credit as well in an exam setting. So I encourage you to write out this step as well. It's not required, but putting these limits together feel like you're really, really busy. Just break it up into small chunks. We have the nth term defined through this structure. We need the n+1th term. So we just go back here, and everywhere you see n, go n+1. So that would be here the exponent, here the base, here the exponent. So an+1 is -1n+1. I'm going to put that alternating part just in the numerator. Or I'm not sure if that was the best call, but let's stick with it. Here we'll go n+1 squared plus 1. Down the denominator is 2 power n plus 1. So that's first part of the ratio test. Indicate what these features are, because we have to take a limit involving them. So now let's go limit as n runs off to infinity. Notice that there's absolute values here. That's how we're getting into a statement of absolutely convergent altogether. The absolute value is incredibly important, so we need to include that to start. So we take the absolute value of n+1th term is always in the numerator for this type of limit. That means we're just penning in this pretty much. I'll go -1n+1 bracket. Over here, let's leave it as is for the moment. n+1 squared plus 1. But then down below, this is a good one to factor down. If it's 2 to the power of n+1, let's rewrite it as 2 to the power of n times 2. That gives us the n+1. Next, we're dividing it by this whole thing. But let's use that common trick that we've been emphasizing a lot, like with the limit comparison test. If you have to divide by something, you can save an awful lot of time and paper just by multiplying by the reciprocal of this one. Think of the -1 power of n belonging into the numerator. That would mean the reciprocal is -1 power of n. You can put it above or below. It'll give you the same effect. But down below with n squared plus 1, that means 2 power of n, since we're taking the reciprocal, is up into the numerator. And we got through that step right there. We now have the limit of the ratios. N plus 1 term, divide by the n term. Any questions at all, folks, to that statement? It looks really bad. So it almost looks like we've been lying all along, that the ratio test is a really nice test, right? Because the limit looks just downright scary in a certain sense. But the thing that really works out for the ratio test is if you form a ratio of the nth term dividing into the next term, you're automatically getting loads of cancellations. Here's the first one. 2 power of n is just gone, so this limit is already a lot easier to compute. Absolute value also enters into the picture, and it's going to wipe out anything that had a negative sign or anything that was alternating. Those portions are gone. And now because n goes off to infinity, absolute value will pass through anything involving just n. This is always positive for all n, and same down below here. So now it's just the limit as n goes off to infinity of this part in the numerator. Let's expand it just for the heck of it to see the limit a little bit better. Expand it, it's n squared plus 2n plus 1 plus 1. So all terms combined, it'd be that in the numerator. Denominator is n squared plus 1. Let's also exhibit some coefficients because we now have a rational function with tie and degree. The limit to this is, thank you. If it comes out as 1, the test has failed, right? That would have been not good on this one, but thanks for spotting that. Another struggle in running this test is there is a lot of stuff, right? You have to remember to capture all the stuff and bring it over. So don't do as I did. Don't forget to write in that last 2. So if there's a 2 there, I should have said times 2 like this. 2n squared plus 2. Let me just distribute it through to show it fully. So I've taken this 2 that I've just ignored, distributed through, 2n squared plus 2. Now with the right values, we have the right limit. So this comes out as 1/2. That was my expectation on this one. Thanks for spotting that 2 that was omitted. Let me put a little box on it as well to show the effect. Once we get through that, we're at this step. We found the limit. We have to do our limit as normal, but these are usually pretty fast limits. When we mention this shortcut, I'm then taking this limit all the way back in section 11.1. It's because we've probably done this shortcut in class at least 30 times by now. It's hard to track these. But any questions at all, folks, getting this limit down? Anyone would like to see it a different way just for the sake of practice? Okay, so now once we get the limit down, we just cite the ratio test again. We're in this situation. The limit is strictly less than 1. Let's just say it here. That gives us the conclusion, absolutely convergent. If you just say this is absolutely convergent, that's totally fine with me. Some people have taken this a little bit further because the instructions say test for convergence or divergence. And the absolute convergence test says if it is absolutely convergent, then it's in fact convergent. But if that feels redundant to you, that's good because then you're thinking absolute convergence always implies convergence. It is the right thought. So I'll give one conclusion going this way. Let's say this implies summation an is absolutely convergent Absolute convergence is just the side effect of that part right there. And if you leave your statement right at that step, absolutely for full credit right here, or hang on, is it for full credit? We never said what test we're using. I mean, it's pretty clear. It's looking at us, but just for the sake of how we solve them on homework and on exams, let's say by the ratio test. So now we've shown all steps of the ratio test. And here's the part that's really totally optional. You never have to do this, but just for the sake of tying together this statement right here, you could say this shows summation an is in fact convergent by the absolute convergence test. Again, it's an orange just as an additional comment. And that's what the absolute convergence test was saying. If you ever say a series has converged absolutely, like we concluded on through the ratio test, then it is feeling redundant, but that means the original series is a convergent one in fact. Well, we did, folks. That's running through the ratio test. Any questions at all getting to that conclusion? Either one, really. Okay, our goal today is practice this some more. So let's grab this test, see what else can happen with it. So it has 3 conclusions, but only 2 of our conclusions that actually help us. If we ever get to limit 1, either we made a mistake on the limit, like I did earlier, or we're just using the wrong test. So that will happen on these notes, but sometimes there's also kind of a dead giveaway of why you would want to use this test in the very first place. Ratio test on this one is absolutely the right choice because of one part, factorial. If a factorial comes up, this test does a fantastic job at handling it. We haven't had factorial come up at all for series, only once for sequences. We've practiced working out limits involving factorials. Really, the reason we practiced factorials in sequences 11.1 is because we were thinking of this. And factorial isn't just a one-off. In Taylor series, Maclaurin series, end of chapter 11, factorial will come up every single time, essentially. So right here, let's indicate that this is factorial. And it is a giveaway that ratio test should be used. That deserves an exclamation mark because that is definitely a bold statement. And now that we're looking at it, what would you all guess? Is this a convergent one or a divergent one with factorial in the numerator, exponential in the denominator? I would agree with divergent. It turns out factorial just totally exceeds the growth rate of any exponential whatsoever. That's kind of an amazing fact. And if this is divergent, why not just do test for divergence? That is a really good thought to have at this moment. Trouble with test for divergence is we're running a limit involving factorial in the numerator, exponential in the denominator. It's indeterminate of type infinity over infinity, but L'Hopital's rule is not here to help us because that function is not continuous at all. It's not differentiable at all. It's a discrete function. It takes inputs the integers and it outputs the integers. You can extend the factorial function to something called a gamma function, which is continuous version, and it does give the factorial on the integers. But now we're getting extra complicated on something that ratio test is just going to run right through it, no problems whatsoever. So again, even if you think that test for divergence could work, that's still a harder test. That's kind of weird, only because of factorial being in the picture. So here's how we're going to run this one. Let's do the same step. Call this summation an, which by its nature has defined that as the nth term. we need the successor term, the n plus 1th term. So we just write it in, an plus 1, change everywhere n occurs into n plus 1. So this will be n plus 1 factorial up into the numerator. We have tricks to handle that though, so we're going to use them here as well. Denominator 7 power n plus 1. And you know what? Let's just simplify this one right here as we're on it. This is going to make the work in the limit a little bit more manageable. N plus 1 factorial can simplify in a lot of different ways. But one way to do it is go n plus 1 times n factorial in that kind of way. Let's make, sorry, say again? Let's see. Yeah, that'd probably be a good one to show because it's going to support the steps on the next stage. So you wouldn't have to show it right here directly, but you'd want to show it when you're going to compute the limit. But you know what, now that I think about that, if you form this limit like this, and you left it as n plus 1 factorial, but you canceled correctly, I'd say that's totally fine as well. But other questions at the moment? Just a reminder on what we did here to here, just in case factorial might be a little bit rusty. It has been a while since 11.1. That was before spring break. If we wrote n plus 1 factorial, then what we mean is we're taking n plus 1 times n minus 1 times n minus 2, all the way through 3 times 2 times 1. So that's the structure of n plus 1 factorial. It just starts on whatever integer is here, descends by 1 and multiplies. But what we could do here is associate. And that way, if we make that association, then we would have n plus 1 multiplying, still in the bracket just to show the association. This is now n descending by 1 on every integer and multiplying, n minus 1, n minus 2. That means the thing in the black is just n factorial again. And that's how we come down to here. Then last thing to do is 7 power n plus 1 is the same as 7 times 7 to the power of n. So now we're thinking this is going to happen. If we're on the money on, it should diverge. By the way, it's often not a bad idea to look before you leap because our expectations mismatch. Maybe we just made a small mistake on the limit. So let's go take limit. As n goes to infinity, I almost forgot to say this was a ratio test, but let's just say it here. Ratio test. It's silly with the test looking up at us, but we're thinking that this could be a homework question context or even an exam question context where we would have to say it. First thing I'll do is just say what we're about to compute. An plus 1 in the numerator, divide by an in the denominator. This helps out with the notes, but these limits feel like there's a lot of stuff. It also allows you to now, at the next step, just use the mathematical procedure of plug and chug. Plug in an plus 1. Here it is in a simplified form. N plus 1, n factorial, 7 times 7 power of n. Then next we multiply by reciprocal of an. So flip this fraction to 7 power of n. Divide by n factorial. After doing all that stuff, you always expect a big set of cancellations. You also have to ask yourself, did I need absolute values at all? No, we probably could have dropped it right on this line because everything is a positive quantity here, but still include them just as a reminder, just in case. It's good to put it here, at least in the formula. Could have been dropped at that step. But more pertinent is the cancellations. The exponential's gone, factorial's gone. All we're doing now is a limit as n goes to infinity of n plus 1 over 7. This time the denominator is bounded, yet the numerator is degree 1 growing without bound. Any volunteers to say the limit on this one? Absolutely. This one is total diverges to infinity in the limit. That's this possibility. It didn't come out as L greater than 1 because the limit wasn't even a finite number. It came out this way. That's included as an or statement, so we still have the right conclusion. Divergence on the original series. So this part right here tells us summation an must diverge. Well, we did it, folks. That's the foregone conclusion on this one. Notice that there really isn't a lot to do. All you're doing is writing down what each one of these components are. If this helps out, then I'd say get in the habit of doing it so that it's a big help on the exam. But if you can just see the structure, look at the series and drop it all in and compute from here, that's fine as well. Any last questions, folks, on dealing with ratio test? Okay, so ratio test handles lots of interesting stuff, like whenever factorial comes into play. The last one was a good call on ratio test because of 2 power of n. Feels like a geoseries with n squared plus 1, not quite the same. So huge mismatch of type of series. And the next one we're looking into is the root test. This one doesn't get used as often in this course, but it does get used every now and then, particularly in this section. So we have to really decide, when are you using the root test? The feature is you're taking a limit involving an nth root. So there's an nth root involved. This part right here is the sole indication the root test is probably the best bet. If n is simultaneously a base and a power, so it's a power on the part where it came in as a base over here, this is another one of those dead giveaways. Let's call this just that part highlighted. Huge giveaway that the root test should be used. So ratio tests look for things that are mixed up too much. So I can't use P series, we can't use geoseries, too much going on, or factorial is the dead giveaway. But this is the indication we ought to try a root test. The root test is a little bit nicer than the ratio test because there's less stuff going on. You're only using an. An plus 1 doesn't even come into the picture. So if we just call this summation an, then we've defined an to be all of this stuff, and we're ready to get going. So here's root test. And the root test, the limit, is as n goes to infinity as before, but we're taking an nth root. You could write out this way if you'd like, power 1 over n, or you could write out just more verbatim in the structure they provided. I'll write it same notation, nth root of the absolute value of an. So that gets us started. Here we're just connecting the dots with what the formula is. What part is an in the formula actually? It's that part. Next, we make a substitution. Take limit n goes to infinity of the nth root. Don't forget there's absolute values here. We have to write that into the next line. Same with ratio test. You know, that's easy enough to forget. Let's make a comment here. Absolute value bar should be here. I'm writing should because I can't say must. If you took the absolute value and just put in the right stuff, then that's okay with me as well. I'll just assume you knew you were taking the absolute value, dropped off that negative right there. Otherwise, it should be there, or else it's easy to forget the negative does in fact have to go away. So on the inside, it's going to be negative 2 power of n plus 1 to the power of 5n. Geez, that's getting a little bit more complicated than I was hoping. Let me extend this a bit. So here's our absolute value bars again. And I want to go with an extra bracket. Like that. Okay, So, sorry, just deciding where this all should go. That should about do the job. First thing I want to do is put in 5 on the inside. Then the n there, that's the whole sole reason why we're doing this test. I want to put on the outside. And this looks really weird, but in the land of exponents, those would multiply together and get us back to the 5n. If I take the exponent of something already raised to a power. I'm putting n clear out there because this is much like something that happened algebraically in exam and homework problems, where if you ever do e to the power of -2 natural log x, no cancellation here either, so I have to be really careful with that 5. N is just essentially going to divide. And over here, you have to be really careful by writing e, natural log x power -2. So at this stage, it cancels, and we get x power -2. That was my thought on this one. At this stage, the nth root cancels this n right here, leaving behind the power 5 still. So we have absolute value bar, something that's to the 5th power. Because it's the 5th power, that negative sign still survives, but absolute value is going to just wipe it out. On the next line, we have that this is equal to limit n goes to infinity of just now 2 power of n plus 1. So what all happened on this? The nth root took off the power n. The absolute values took off the negative sign. Now the limit can be done just immediately by visual inspection. Limit is, any volunteers? 2 exactly. Thanks for indicating it. We have a limit of 2, which puts us in this situation right here. Our limit exceeded 1 and it's finite. If it's infinity, same situation. It's equally just divergent. But to keep these tests in line, let's write in greater than 1, just as a reminder that it's this part now, which implies summation an diverges. So nothing more to show on that one. Weird kind of test, right? Usually all the fighting is right here, carefully analyzing what cancels, what carries down. Then it's a short limit after cancellation, fast conclusion. Any questions at all, folks? Finalizing this one.
What happened with this one?
Oh, good question on that. I think I just totally forgot it was there. That 5th power should still be there. So power 5 survives. Thanks for spotting that error on that one. Power 5 came from up here. It affects the limit, but not the conclusion. Let's fix our limit so our conclusion looks a little bit more reliable at the same time. Let me take this and say that this is not actually 2. This is 2 power 5 altogether. What I've done here is I've used the idea of continuity. Rational functions continuous at all n, since our domain excludes negative values. Limit goes on the inside, and the limit of that is 2. Thanks for the tie in degree above and below. Thanks for finding that power 5. That tells us the output to the limit is actually 32. Let me count them off. 2, 4, 8, 16. Yeah, 32 altogether. Still exceeds 1, but that is an important quantity to get captured in. Exceeds 1. Now our conclusion looks a little bit more believable. I mean, if you make a mistake somewhere, it feels like the whole thing is off. So now we have summation an diverges. Other questions at the moment, or any weird omissions that you can see? Okay, well, with any kind of problem, we need to run through it more than once to get a good feel for this. So let's try this out again. Here's run 2. So another root test. This one has some other weird things going on with the exponents. Aside from that, I think this one is maybe a little bit nicer than the prior one we took a look into by just a little bit. So once again, let's say what is the dead giveaway that we would want to use this test. It's right here. Let me blow that up just a bit. So this part and this part are the giveaway. For root test. So those two pieces specifically would tell me I would never want to try to analyze this in the normal way. Basically, n to power of n, n plus 1 to power of n, these things are nasty. We want to correct this for sure to get it started. Let me fix my arrows though. So let's first give this a name. Let's call it summation an, which effectively redefines all of this stuff right here. It's not even in a very good format to even really use that ratio test. I'm not sure what I'm doing with the color coding. I just want my color coding for the arrows to survive, but that should do the job. Let's go an equals. Now, to really use the ratio test in this situation, it's kind of like what goes on with the geometric series test. You want your thing that looks like a ratio to be under one common exponent. It doesn't have to be n minus 1. We want it to be n exactly, so the nth root can cancel in a nice way. So 2 power of n plus 3 is not super convenient, but we can fix it. N plus 1 power of n, that's actually good for us. So first thing we do on this numerator is just factor out 2 power 3. Leaves behind 2 power of n, then n plus 1 over power of n. Then you could take just one additional step to organize this a little bit better. 2 power 3 is 8. And it's going to be multiplying the fraction 2 to the nth power divided by n plus 1 to the nth power. So that's how that part would go. And then last, we get 8 over 2 to the power n plus 1 to the nth power. So that's what this all is in a more nicer format for the root test. And now that we're looking at this, what would y'all say should happen? Does this look like convergence or divergence on part B? This one is a little bit harder for me to tell. It's exponential the numerator, not exponential the denominator, because the base is also increasing all at the same time. If I would give a wild guess, I think the denominator is growing a lot faster because the base increases as well as the exponent. But that would be a guess. I'd say probably converges. I wouldn't be too surprised if it diverges, though. Let's see what happens. This, though, makes it look like it probably does converge. If I'm looking over here, I'm a bit confused. But over here, when n gets big, it's informing us more correctly that the base is getting small, while the exponent gets big at the same time. It's looking more complicated. If I'm looking at this, I'm more on the fence than if I was looking over here. Kind of a weird one. What's going to resolve it all the way? The root test is going to leave us no question on convergence, divergence, unless we're in this output. We'll see an example of when this happens in these notes, when we have just inconclusive altogether. So let's hit this with now root test, which means we're taking the limit. As n heads off to infinity of the nth root of the absolute value of an, which is now limit, n goes to infinity. Now we need absolute values here, it's part of the formula, but looking at what we're plugging in, absolute value isn't going to do a bit of difference to that. It's purely positive, so I would drop it on the next step. It's redundant to bring in absolute value again. I'll just write in nth root of 8. Let me fix my 8. Should be outside. 8 times 2 to the power n plus 1 to power n. Something that's kind of weird on this is when I go to take the nth root in the numerator, excuse me, not in the numerator, but rather the limit's going to come out as limit n goes to infinity. We'll have the nth root of 8 over here. Then over here is a cancellation, where this just knocks off the exponent, so it's going to be times 2 over n plus 1. That nth root of 8 makes me really nervous because taking a limit involving this might use some non-standard methods. But having n plus 1 in the denominator takes away the nervousness for sure. Let's maybe reformat this. It can also re-expressed as limit n goes to infinity. I'm only taking the step to get a really good look at what's happening in the numerator. 2 times nth root of 8. Denominator is n plus 1. We should be able to do this limit. So let's imagine what happens to the nth root of 8. If it's the square root of, let's say 9, just because it's an easier number, it would have been a 3. If it's the cube root of 9, it's even smaller. Would you all agree with that assessment? I agree, yeah. The higher the root, the smaller the number. Let's just run a quick numerical experiment. So if we go 8 power 1 divided by n, we're taking nth roots. If n is 1, let's go from 2 to 10, step size 1 to make some sense out of this. So if n is 2, we get, oh, forgot how to work this. When n is 2, we get 2.82. Let me fix this. Let's really start it at 1. Okay, so when n is 1, we get 8. That's a better starting point. If n increments by 1, forgot that place. If it increments by 1, we're taking the square root, 2.82. This is the cube root. Cube root of 8 is 2, but it's going down. And the higher the root we take, the smaller it gets. This one looks like it really would have a limit. I believe the limit of something like this should be a 1. And we can kind of see that by making this be like the millionth root of 8 is very close to 1. But if I'm trying to show that as a limit, that's still really hard. But here's what we get from that numerical experiment. Numerator is in fact bounded. The numerator doesn't go above, say, nth root of 8. When n is 2, oh geez, that's hard. Nth root of 8 when n was 2, which is 2.82. That is telling me that the numerator is less than 6, always. It only gets smaller as n increases. So let's add a quick comment there. Always less than 6. Bounded. Whenever we get a bounded sequence like that, that's exciting when we're taking a limit, because now we can say the numerator is bounded, never bigger than 6. If the denominator is just getting bigger, growing without bound, and is going to infinity, this is the foregone conclusion. Limit has to be 0 exactly on this one. Well, is that allowed? The limit has to come out as L. It just has to be less than 1. 0 is allowed on this one. But if you felt like that was sketchy, good on you, because it is sketchy, say, right over here in the limit comparison test. The limit comparison test had to be strictly positive. This is one of the ways that these tests are really kind of tricky. That's why this is a handout on an exam, because these conditions, they don't necessarily look like they're compatible with each other as you go from test to test to test. Really easy to get confused on that. But we're in this situation. Looks like this was convergence on this. Zero in the limit. It's a good idea to say it's less than 1, just as a reminder. But this part gives condition on convergence now. Now, ordinary convergence, the stronger kind, we have now that this implies summation an converges absolutely. Not that we're extra sure that it converges, but it converges in the sense that it's a stronger convergence than conditional convergence that we've seen happen as well. Well, any questions, folks, with running through the root test scenarios? Okay, so these were just a couple of really fast problems, both for ratio test, root test, just to get a feel for how these brand new tests go. Now, last set of problems, are just a small set of mixed exercises. Here, we still want to use ratio test and root test, but now our goal is to decide which one is the correct one, and what do we do if a test fails, because that can happen on this list of notes. First one, however, 10 power of n might tell you it feels like it could be a root test, but the factorial has precedence on this. Any factorial that occurs, your first thought ought to be try the ratio test for this one. So because of this part right here, we'll say use the ratio test. That means we have a definite process for this. We can call this summation an, which has now defined the nth term in that test. We'll be running limit n off to infinity. And we've got the denominator already. An goes down there. I mean, we know what it is. We have to write it in. Numerator of that is going to be an plus 1. So we get an plus 1 in this way. Considering the nth term here by the red dot, the successor to that term, an plus 1, is we go -1. It's n plus 1 already, so that's n plus 2. The absolute value is just going to wipe this thing out already. So even though that's a weird thing to look at, you could simplify this. I'd say just keep on going. It's just going to die off. We have another n factorial occurring, so this is going to be n plus 1 factorial. Denominator is 10 power of n plus 1. Well, any questions, folks, on the successor term? Okay, I'm running out of horizontal space, so I'll simplify it back down in here, back inside the limit structure. It's now the limit as n goes to infinity. This time we really do need absolute value bars. They're going to serve a really important function, wiping out these things. So just write in an directly. -1, n plus 2. Well, let's also factor this one down. N plus 1 factorial factors as n plus 1 times n factorial, which is pretty much the standard thing you would do each and every time for this kind of series when n factorial comes in. Usually you want to factor this as well, so let's go 10 times 10 power of n. And that's an plus 1 with just a couple factoring steps. An is in the denominator, so don't forget you have to flip this fraction. You'll know you didn't flip it when nothing is canceling and it's just gotten way, way complicated. So that would be a good indication. 10 power of n on the top, -1 power of n plus 1 times n factorial on the bottom. This time directly copied in for blue. Then we do the very satisfying step of killing off everything that gets wiped out. First by absolute value bars, those are gone. Cancellation removes the exponential function directly, and it even removes the factorial function. So it's as if this was the world's best test because everything about this series that was difficult is now gone. So that's why we call this an extremely powerful tool. It eliminates the messy parts of the series. We're now looking at the limit as n goes to infinity. Absolute value has served its role, but make sure I don't forget to copy everything down. That has been my mistake today. N plus 1 is still alive in the numerator. Completely to the right, everything's gone, but we still have that 10 in a denominator. So now, even though you might have looked at this and thought to yourself, factorial is in the numerator, there's no way it converges with just an exponential in the denominator. But we really had to show those steps, so these are those steps being shown. Now here, this time bounded in the denominator, numerator unbounded, headed towards infinity means limit itself is infinity, but that's okay in the ratio test. Let's pull it up just briefly this time. In the ratio test, we're in case 2 with a situation the limit is infinity. That means all we have to say is it diverges. Here, I'll just say it plainly this way. Diverges. On the last problems, we often said summation an converges or summation an diverges, but you know what? This is a nice conclusion because we never defined a second series. It was all about AN in the first place. However, if you have, say, this going on, where you're dealing with two series, one for AN, one for BN, that's when it's a good idea to actually say summation BN converges when you get to that conclusion, summation AN converges when you get to that conclusion, because there's way more moving parts. The short of this is, when you get to the ratio test and root test, our work on sequences and series is actually becoming a little bit more simplified. We're over the hump by the time we're over the comparison tests. Those were the rougher ones, I'd say. Well, let's try this out again. -1 power n minus 1 divided by 3 power n plus 1. Any volunteers for a test to try out on that one down below? Good call. The alternating series test is the right test to use on this one. And it doesn't even feel like it's in the right section though, right? If you see this come up in the homework, and it's a possibility for something like this, you might be tempted to use the ratio test. It doesn't work. But you know what? We should show that because it's also informative to know what happens if the ratio test has failed, or if it's inconclusive, the different way we wrote in on the notes. What does it look like? It means that when we looked at the series, nothing really jumped out at us of needing the most powerful test. If we're really looking at the summary of tests for series, we should always start at the very top, find the one that fits it the best. And it really is the alternating series test on this one. It's been a while, so we'll cover this one really carefully and make that our official method. But just for the sake of seeing what goes wrong, like we said, let's in fact do it with the ratio test. This is a common thing that can happen in this homework section because, again, the ratio test is just sitting there. It's tempting to use it. But we have to know not every time is the ratio test a good call. And this is one of those times. Let's give it a try, see what goes wrong on it. Then we'll analyze it correctly in part B. Now, if this was an exam problem and you did the ratio test and you said the ratio test fails, and you didn't have enough time to come back to it, just leave it all on paper. I would still give a lot of partial credit in that scenario. If it was a 10-point question and you got to everything right, ratio test fails, ran out of time to come back to it, you'd probably get either 7 or 8 points out of the 10-point question because all those steps would be correct, as well as the conclusion. You'd only lose points because the test failed. It wasn't the right test, literally. So let's give this one a try. Let's call it summation AN through the ratio test, which is now defined all of this stuff. Let's next define AN plus 1. That's going to be, looking over here, -1 to the power of n plus 1 minus 1. So now just n. Putting n plus 1 down below there, so 3, n plus 1 plus 1. Then we just do this limit here, where the red dot is. Limit as n goes to infinity. AN plus 1 divided by AN is now a limit. As n goes to infinity, absolute value of the structure, -1 power of n. Let's just combine like terms, 3n plus 3 plus 1, so 3n plus 4 times reciprocal of that part, so 3n plus 1 over -1n minus 1. At this stage, it might not be super clear what goes wrong, but if we cancel, it becomes obvious. So let's do the absolute value cancellations, those parts. What remains is not negative for any value of n as it goes to infinity, so we'll drop absolute value now. We have limit as n goes to infinity, 3n plus 1 over 3n plus 4. But that's a fast limit, right? We have Italian degree as usual for a rational function. The limit comes out as 3 over 3, which is 1. So the moment you got to this step, you might have been nervous. Things are not actually working as intended. We are in this situation. The limit has come out as 1, which means ratio test. You can either say has failed, like it's written into the notes. In the new edition of the textbook, our author has changed has failed to is inconclusive, but you're saying the same exact thing. Let's go with is inconclusive. This just means we know nothing about the series by using the test. It might converge, it might diverge. But you know what made it inconclusive, really? It kind of converges, actually, but it does not converge absolutely. This is the one shortcoming of the ratio test and the root test. Its conclusion is for absolute convergence, and you might miss the weaker form of convergence, the conditional one. However, go down to the alternating series test. It has a different conclusion as well, just ordinary convergence, not the strong brand of absolute convergence, unfortunately. Yeah, go ahead.
Does the logic go both ways? That like, if it's less than 1, then it's absolute conversion, but it's also true that every absolute conversion thing will result in less than 1.
Yes, absolutely. So anything that would converge absolutely. Hang on, let me think about that logic. Yeah, that is a good question. Once I really think about the logic going backwards, I'm going to need to come back to that. It sounds plausibly true, but we know if we switch the order of the logic, things don't go wrong. I'll come back to this one when we are on Wednesday's class. And the question is along these lines. Let me know if I didn't capture it entirely. So let's say here, if a series is known to converge absolutely as a given. So we have this given extra information. We've run no tests whatsoever. Then will it be true that the ratio test will output a limit L less than 1 for a correct conclusion on absolute convergence? So my guess, yes, but we definitely need to look into that. So I'll come back with a legitimate homework assignment, let you know what the outcome is on that. The problem with really committing to a yes on this is series are weird, and it's easy to write out a really, really weird one. Some examples of counterexamples analysis go natural log of natural log of natural log of natural log n. I'm not joking, weird functions that provide the right counterexample where that flips to no. There might be one in this kind of situation as well. So I would say yes for most routine series, but there might be a possibility that it breaks down for just the right one. But other questions so far?
It would be best practice to also do the absolute value of the absolute conversion test part of it.
So if we're thinking the series is known to converge absolutely, I would say in that case, if you did use the absolute convergence test, you would just be reduplicating this result right here. What we wonder though is,
in case of this question.
Oh, in this question right here?
Yeah.
So if we use absolute convergence test on this one right here, it would diverge because it doesn't converge absolutely. So if we hit it with that one, that means we'd be taking the absolute value of what's this whole thing is. Our new series is just going to be 1 over 3n plus 1, which we could compare to the harmonic series 1 over n and get a good divergence conclusion on that one. So absolute convergence test on this one would fail as well because it wouldn't have this part satisfied. It would diverge at that step.
Do we also have to show that one?
Sorry, say again?
Do we also have to show that?
No, not in this situation. Yeah. Yeah, if all we're doing is just testing this series and we're trying to get out of inconclusive, alternating series test will do the full job for us for this one. Other questions so far? Okay, definitely a weird one, right? And really the whole purpose to this example is just to know when ratio test really falls down. If you know something just really looks like an honest P series, an honest geometric series, then the ratio test is going to give you this outcome each and every time for all P series, all geo series. And that's why we're emphasizing alternating series test yet again. So here is our attempt 2. Well, really, this is attempt 1. As Brian mentioned, this would be the one we want to go to first. But we got the failure of the ratio test out of the way. So here's our second run. When we go to use now the alternating series test, extremely rapid. So what we do is we pick up a Bn. Bn is going to be 1 over the 3n plus 1 that we see right here. So let's say let Bn equal 1 over 3n plus 1. So we're extracting the purely positive portion of the alternating series. Next, we have to make 2 conclusions. First one is that this should be decreasing. Absolutely is with bounds in the numerator and growing in the denominator. So let's say here, then Bn n equals 1 to infinity is a decreasing sequence. And step 2 we have to show is the actual limit itself right over here. Limit as n goes to infinity of Bn. There's really not much to write here. Even if I do this substitution step, there's still not much to write. We are back to bound in the numerator, growing without bound down below. So this limit comes out as 0, and it must. But once you meet those 2 conclusions, we get to say the original series, summation an, converges. So this means summation an converges. That feels redundant, but we got it, folks. That's the conclusion on that one there. Any last questions so far on finalizing this one here? It's definitely a weird one-off one. We have a conclusion of convergence, but now going back to an earlier question, here the whole question itself was determine convergence or divergence. But if you're thinking about this one in terms of what we did just last class, a little last Thursday, a while ago, relative homework assignment 11.5, the question looked like this instead. Determine whether the series is absolutely convergent, conditionally convergent, or divergent, then you really would want to do another step. We found it converges, but we don't know the flavor of convergence. We would want to take the absolute value of this one, show it diverges, and we would get the extra information. It converges only conditionally. But this problem wasn't about the trichotomy. It just wants to know convergence of any kind, so we ended it right at this step. When we come back next class, we'll go for this final example right down here. This is the last one on the page, but it'll be a good one to come back to fresh to review ratio test, root test once more, because we haven't used the root test as much. Any last questions at all, folks, before we call tonight? Okay, have a great evening, everyone. We'll come back, finish off 11.6. Then we're going to take these 2 things, primarily the ratio test, and get into power series for the first time. So finally, we're switching gears into a slightly new concept.
Yeah, I thought it was asking for permission. Yeah, that is where it's.